Wisconsin.
Oh, right.
Exactly. Yeah.
And then your postdoc, I forgot.
Princeton, PCTS, and Lyman
Right.
Spitzer Jr. Yeah. I also spent a year in Cambridge.
Oh, what do you got?
I had a master's degree
Oh,
in between undergrad and PhD.
after.
Yeah, yeah.
The Wisconsin.
I don't.
No.
Yeah. You know, some people say they claim that I have a very slight French accent,
Yeah.
but no one's ever told me that without knowing that I was French beforehand. So I think it's a bias. Yeah, yeah. I don't think it's real.
I have a French accent when you say croissant.
A croissant.
All right, ready?
Sure. You want to use my mic?
Welcome, everybody. Our spoken speaker today is Daniel Lecoanet from Northwestern University, but moving to CPA sometime this year. Daniel's originally from Wisconsin, went to the University of Wisconsin, and the Cambridge for a year, then did his PhD at Berkeley, working with Elliot Fires, which makes him Kareem's academic older brother. Speaking of Kareem, we're going to have a little campaign toast. We're celebrating the MacArthur Fellowship. So stick around, that'll be part of the money afterwards. And then went to Princeton, CPS Fellowship, before starting faculty job at Northwestern. And Daniel works on all kinds of different problems in fluid dynamics and hydrodynamics. Everything from tanks of water to, core convection in massive stars. There's so many underlying similarities in physics and so many problems works on. A lot of overlap with things I'm interested, waves and stars and magnetic dynamos. And we're going to learn about some of those things, probably not all of them. Daniel also works with Earth's atmosphere, heliophysics, so there's kind of limitless applications of physics. We'll hear about some of those today.
Great. Thank you so much, Jim, and thanks for the invitation. It's been great chatting with people. So exactly as Jim noted, I'm going to be talking about some multidimensional physics that is important for stars, but as we'll see, is also important in many other systems. And I'll be using various different techniques to try to study these problems, ranging from theory, simulations, to even some laboratory experiments. This work is in collaboration with Michael Lebaus, so a long-term collaborator of mine at CIERA in Marseille, France, and also with some people who I worked with when they were postdocs, Louis Couston, who was also at CIERA, now he's at Université de Lyon, then Evan Anders and Adam German, who are now both at Anthropic, making lots of money, and many others I'll mention as we go along. So I want to first start talking about stars. So if you look out in the sky, one of the things that you see is stars. And when you look at stars, there's a couple of things that you might notice. One is that they have different colors. So sometimes they're redder, sometimes they're bluer. And then they also have different brightnesses. And this is kind of the way in which people have traditionally studied stars. The color and brightness, those are two zero-dimensional pieces of data, so it only gives you so much information. Really, what we want to expand the dimensionality of these data sets so that we can learn more. And the first way that this was done was by looking at spectra. So here's an example of a spectrum of a star. Okay, so now it's quiz time. Can anyone look at this spectrum and identify what kind of star it is? Any spectroscopers? No guesses? Yeah? It's not a. That's correct. Yeah, it's not an M dwarf. Very good, very good. Any other guesses? The dashed lines are showing different peaks. Okay, and they'll be labeled in a second, but I want to see if anyone can identify what they are. You think it's a hot star? Yeah, that's right. Yeah. Okay. So this is thought to be a stripped star. So what we're seeing is lots of helium lines. So it's a star that so normally the star of this type would have a helium core and then a hydrogen envelope, but the hydrogen envelope got stripped by a companion. So what you see left over is the helium. Okay. So this is an example of getting information about the star by looking at its spectrum. Another thing that people have done more recently is to look at the brightness not just at a single time, but as a function of time. So this is the light curve of a star, and what the key thing is that the spectrum tells you a lot about what's going on at the surface, but the light curve, the brightness as a function of time, tells you a lot about the interior. So if you're interested in stellar structure, combining these two, and in particular using the brightness as a function of time, can tell you a lot about the interior structure of the star. So why are we doing this? Well, this has really been possible recently due to high precision space missions, where we have a very high precision measurements of the photometric variability of stars. So an example would be TESS or Kepler, soon Plato. These are nominally things that are trying to find exoplanets orbiting these stars via the transit method. But in addition to being good at characterizing exoplanets, they're also great at studying the stars themselves. So as an example, these are 6 different stars that were measured with a Kepler satellite. I think this is part of the K2 mission. And you can see that the brightness of the star as a function of time shows some regular variability. And if you take the Fourier transform of that, you can see that there are many different discrete oscillation modes. Okay. So what are these? It's because the star is some fluid body and it has global oscillation modes. So there's processes in the star that's exciting these modes. And once we have these data, we can do an inverse problem. You can ask, what's the structure of a star that has these oscillation modes? And then it tells you a lot about the interior structure of stars like these. Okay, so this is known as asteroseismology. Okay, now I want to say, like, why should you care? Stars are everywhere in the universe, and they're connected to many different types of astronomical phenomena. Stars are the progenitors of supernova. They host exoplanets, and they're also the progenitors of compact objects. So if you're interested in any of these things, you should also be interested in stars. And indeed, some of the main questions associated with these different astrophysical phenomena are actually questions that tie quite sensitively to stars themselves. So, for example, an interesting question for supernova is what's the chemical yields of supernova? For exoplanets, of course, people are very interested in habitability, and one aspect of habitability is probably linked to the magnetic cycles of the host stars. If you're constantly launching flares at your exoplanet, that's probably not great for life. And one of the things that's being probed with gravitational wave observations of compact object mergers has to do with the spins of black holes and neutron stars. And all these different things are tied to the underlying stars that were progenitors of these objects, or hosts of exoplanets. And they're really intrinsically linked to some of the unknown processes that we're still trying to characterize about stars. So in particular, supernova yields are very sensitively linked to the chemical transport within stars. Magnetic cycles come from the magnetic dynamos, and in order to understand the initial spins of black holes and neutron stars, we really want to better understand the angular momentum transport in stars. And interestingly enough, all of these processes have recently been probed to greater detail than ever before using asteroseismology. So I want to mention each of these in a little bit greater depth. So the first has to do with chemical transport. So I had showed you these light curves for 6 different stars, and those have different oscillation modes. So those oscillation modes correspond to gravity waves, and gravity waves have so what we measure about the oscillation mode is the frequency, or equivalently the period of the oscillation mode. Normally, if there was nothing else going on in the star, the period spacing between adjacent gravity modes would be constant with periods. So if that was the case, then each of these curves would be straight lines. Okay. In many cases, you can see that there's this downward trend. That has to do with the rotation of the star. So the faster the star is rotating, it means that these period spacings between adjacent modes trends downwards. So you can see among these 6, this one is the rotation is least important. The other effect that you can see is that there's these dips in the period spacing diagrams. And it turns out that that's actually very sensitively linked to the chemical composition gradients that are occurring in these stars. So by looking at these data, we can compare to structure models of stars and say a lot about the chemical composition structure inside the star, because it's linked to very carefully these dips that we see in these period spacing diagrams. So this is giving us a lot of information about chemical transport in stars. Another way that we've learned about stars is through probing angular momentum transport, and that's because we can now, for the first time, measure what's the rotation rate of a star, not just at its surface, but also in its deep interior. What's being shown here is oscillation modes associated with a sound wave, or P mode. And these oscillation modes are I mean, the structure of the star is predominantly spherically symmetric. So you can decompose the waves into spherical harmonics. And an L equals 1, a dipole oscillation, has 3 different spherical harmonics associated with it. It's given by the different azimuthal wave numbers, -1, 0, and +1. And if a star is rotating, then the dipole mode is split into a triplet, as is shown here. So this is the m equals 0 piece of the triplet, this is the m equals +1, and this is the m equals -1. And this frequency spacing between the -1 and +1 is related to the rotation rate of the star. But that's the rotation rate at the spot where the wave spends most of its time. And for certain stars, we're lucky we have certain waves which spend most of the time near the envelope, other waves which are mostly in the core. So through that, we can measure what the rotation rate is in different parts of the star, and that tells us a lot about angular momentum transport. Okay, then the last one that I want to discuss is magnetic fields. This is something that Jim's worked on quite a bit, actually. So what's being shown here is the frequency spectrum for 2 different red giant branch stars, and in this first one, what a typical spectrum looks like, you get all these different oscillation modes. Through some modeling, they have identified certain modes as being dipole modes, as shown in red. This other star, if you look at the blue, those are the radial oscillations, or the excuse me, black is the radial oscillations, blue is the quadrupole oscillations. Those are very similar between these two stars. So it's both similar frequencies and similar magnitudes, similar amplitudes. And because of that, we think that these two stars have very similar properties, which is to say that they're about the same mass, about the same age. But there's a big difference. You can see that this one doesn't have any L=1 oscillations. And Jim actually first suggested that that might be to the presence of a large-scale magnetic field in the core of this star that's not present in this star. Okay? So the idea here is that noticing the missing L=1 dipole modes might be a way to infer the presence of a strong magnetic field in this star, which is not present in this star. So that's maybe like an indirect way to learn about the magnetic fields in these stars. Something that's a little bit more direct is that over the past several years, we've been able to look at these frequency splittings due to magnetic fields. Rotation, the leading order will split a mode symmetrically. So what I had shown before, you had the m=0 oscillation, and then on both sides, you had that many equals plus and minus 1. With the magnetic field, that's no longer the case, and you expect to have a special type of asymmetric frequency splitting. And using this, people have been able to measure magnetic fields in the cores of red giant branch stars. So these are kind of the ways in which we've been able to use asteroseismology to give us more information about some of these key stellar processes, chemical transport, angular momentum transport, and magnetic fields that are so important for many other problems in astrophysics. However, we only have so much data. I mean, we're getting more and more every day, but we would also like to have some better theoretical modeling of what's going on in these stars, in part because it's very useful for interpreting these data. So how do we model these stars? Well, the central problem in modeling stars is that there's a very large range of spatial and temporal scales. So if you consider a 10 solar mass star, a main sequence 10 solar mass star, typical radius is going to be about 3 × 10 to the 11 centimeters. These stars have convective cores. The radius of the convection zone is going to be about 6 × 10 to the 10 centimeters. So it's about 20% of the star. If you're interested in chemical transport, one of the major unknown processes associated with chemical transport is how do chemicals get moved from within the convection zone, where things are well mixed, to outside the convection zone. A typical length scale associated with that is called the overshoot length scale, and that's going to be much smaller, about 6 × 10 to the 7 centimeters. So if you're interested in chemical transport and you want to model a star, for sure you need to capture this range of scales, which is already quite large. Okay? But there's even smaller scales. There's the thermal diffusion scale, which is given here. And in terms of fluid dynamics, the smallest scale that might be important in the problem would be the viscous scale. So there's really nothing going on smaller than the viscous scale, and that's all the way down at 3 meters. Okay. So if you wanted to have like a full comprehensive fluid description of a 10 solar mass star, you would need to span 10 to 9 scale separation. Okay. Now you might say, well, that sounds pretty hard now, but the computers are getting better and better every day. Maybe we can't do this now, but in the future, maybe we will be able to. So there was a really interesting estimate done by mentioned in this paper by Steve Tobias in 2021. The estimate actually comes from Petri Kapala, where they asked, with the current computer hardware, or the hardware we had in 2021, what's the power requirement that would be necessary in order to simulate this range of scales? Okay, so that's to say, okay, let's assume that we get a larger and larger computer. Let's not worry about the size of the computer. Let's just see how much power that would take. It turns out it's 10 to the 22 watts, which for comparison is the entire power output of an M dwarf. Okay, so the good news is that at least it's smaller than the 10 solar mass star. Okay, so we've made some progress. Okay, but until we've been able to harness the entire power output of an M dwarf, we're not going to be able to do a real simulation of this. Okay, and even if we could use all that power, I don't think that the best thing we should use it on is running a simulation of a star. And indeed, even if we did, it wouldn't even be so useful, because this is the power output that you would need in order to evolve the star 1 second forward in time every second of real time. But like the star's already doing that, right? So that's actually not very useful. What we would really like is to be able to evolve the stars on evolutionary timescales, which are much longer. So that's what I want to mention next. Kind of what timescales we want to understand. So the shortest timescale is going to be the dynamical timescale, which is of order 100 seconds. Then if you're interested in the gravity waves of these stars, those have typical timescales that are going to be a bit larger. The convective timescale for one of these stars is about a week, so 10 to the 6 seconds. But what's really challenging is that there's this huge timescale separation between millions and the thermal time, or the Kelvin-Helmholtz timescale. So this is a factor of 1 million. Okay, so if we want to understand what's the thermally equilibrated structure of a star, we have to deal with this timescale separation of at least a factor of 1 million. And again, what we really want to understand is the evolution, which occurs on the nuclear timescale, which is even longer. Okay? So really, a 0.1 mass star isn't enough to really tell us about the evolution of stars. If you wanted to do a simulation of the whole star, for that you would need to speed it up by many more orders of magnitude. But despite the fact that there's this huge range in timescales, we can actually use that to our advantage. So if we're interested in the evolution of stars on the nuclear timescale, the fact that that's so much longer than tells us that the star will be in thermal equilibrium, and that it's so much larger than the dynamical timescale means that the star will be in hydrostatic equilibrium. And this is really the basis of the one-dimensional modeling of stars. So the simplest way to think of a star is it being spherically symmetric, where we want to keep track of what the density, pressure, temperature, and chemical species are as a function of radius and time. And we use the fact that the star is still leading order in hydrostatic balance and thermal equilibrium because of this strong timescale separation. Okay, so the dynamics here then comes from the evolution of the different chemical species. Those are created and removed by nuclear reactions. So that's the source term here. But another important process is that there's some internal physics which is moving the chemical species around. And in stellar evolution models, for instance, MESA, that's normally treated in a diffusion approximation. So the real question becomes, what's used for this diffusion coefficient? Okay, this is the question of chemical transport. Okay, so if we can understand chemical transport better, then we can model this diffusion coefficient better. Unfortunately, that chemical transport comes from multidimensional processes. So that's where we have to add some more physics in to try to figure out how to model this best. So that's chemical transport. Then you have angular momentum transport. So for that, you with an equation that sets what the rotation rate is as a function of radius and time, and then including magnetic fields is a whole nother story. Okay, so this is kind of the way that we normally think about stars through this one-dimensional spherically symmetric structure. But in order to make these stellar structure models more accurate and to make predictions about what we expect to see up there in the universe, we really need to be able to understand what these transport mechanisms look like. So that's what I'm going to discuss in the rest of my talk. So I'm going to just briefly mention chemical transport and dynamos, and then spend most of my time on angular momentum transport. So one of the most important chemical transport mechanisms that's still quite unknown has to do with convective overshoot. So if you have a massive star, on the main sequence, the core of the star is convective, and then the envelope is radiative. Convection is going to be able to very efficiently homogenize the material, and as the star evolves, you're going to build up more and more helium in the convection zone, whereas the envelope is still going to be mostly hydrogen. The big question is how much mixing do you get from the hydrogen in the envelope into the core, because that's bringing fresh fuel into the core, and that's going to have very large implications for the life of the star. So as an example, there are some recent papers that looked at different plausible models for this convective overshoot process, the efficiency by which you can mix in fresh hydrogen fuel into the core, and found that amongst different prescriptions of convective overshoot that are actually being used in 1D stellar modeling, there can be up to 50% changes in the carbon and oxygen core mass. So that's like a huge uncertainty in the amount of carbon and oxygen that's being produced in these stars. And then if you're looking even further down the line in the evolution of the star, especially for massive stars, if you put this into a population synthesis code and try to estimate binary black hole merger rates, there can be uncertainties of up to a factor of 100 in those merger rates, just due to differences in convective overshoot parameterizations. Okay? So this is currently a major uncertainty in stellar evolution that is then having major implications in other astrophysical problems. So this is something that I worked on a bit with Vin Anders and Adam German. So what we did was that we ran some numerical simulations. This is with the Dedalus code that I'll mention later. See if I can. I thought that this would be a movie. There we go. Okay. So this is a simulation that we ran. So it's a very idealized simulation. It's in Cartesian geometry. So not the spherical geometry of a star. But in this simulation, the bottom part is convective and the top part is radiative. And you can see that the convective motions basically make it to this spot right here. Normally, when we model stars, we think that the boundary of the convection zone is given by the so-called Schwarzschild criterion, and that's this dashed line right here. Okay? But what happens if you actually run a simulation is that we find that the fluid dynamics actually doesn't care about the Schwarzschild criterion. That these convective flows are able to make it much beyond the Schwarzschild boundary and are able to increase the size of the convection zone by about 10 to 20%. And this actually matches with some of the latest asteroseismic observations, which suggest that the convective cores of these massive stars are much larger than you would expect if there was no convective overshoot. So this process was actually, I mean, I think that the best simulation evidence that we have for this, but was actually theorized quite a while ago by Jean-Paul Zahn. He called this convective penetration. So this is a paper in 1990. And so something that I thought was interesting was that in the introduction of his paper, he talks about this idea of convective penetration, motions that go beyond that kind of break the Schwarzschild criterion. And he actually notes that this has been about in many other fields. But he says that one reason that we astrophysicists too often neglect to confront our problems with those of our colleagues in geophysics and fluid dynamics, although they study similar cases and are often decades ahead of us. So this is something that people have been thinking about in other fields, and something that I found to be very useful is to talk to geophysicists, fluid dynamicists, and others in other fields to get some of the ideas of how they study these types of problems and try to be able to apply that to astrophysics. So I'll give a more concrete example of that what follows. First, I want to say a little bit about dynamos. So I just want to highlight one recent on dynamos. This is the sun's dynamo, which I think is humanity's most interesting dynamo. This work actually came out in 2024. About May, I think May or so, 2024. There was actually just a huge solar flare that hit the Earth, produced aurora. I don't think you could see it down here, but you could definitely see it in parts of California. Due to the sun's magnetic field, there's lots of theories about the sun's magnetic field, where it comes from, where it's generated. I don't find any of them to be very convincing, which is to say that I don't think that that many of them make predictions that have held up to real observations very well. In this paper, we have a new idea by noticing that if you look at the rotation rate as a function of radius and latitude in the sun, we think that shear, so gradients in the rotation rate are very useful for generating magnetic field. The strongest shear is actually not at the base of the convection zone, the so-called tachocline, where many people think that the sun's magnetic field is generated, but the strongest shear actually occurs near the surface, the so-called near-surface shear layer, which has the strongest shear in the sun. And the key thing is that the shear there is negative, and as many of you know, when you have negative shear in the presence of a magnetic field, that's exactly what you need for the magnetorotational instability. So in this work, we did the first global calculations, looking to see whether or not there's magnetorotational instability in the outer layers of the sun, and indeed there are. And the properties of those modes, their spatial structure, time scales, some of which are displayed here, seem to show some features that are very similar to what we observe in the solar dynamo cycle. So we think that this might be some evidence that perhaps the sun's magnetic field is generated near the surface, not near the base of the convection zone, as had been previously theorized. Yes. So I guess the point is that the strongest fields are kind of at mid latitudes, which is exactly where we first see sunspots at the beginning of the solar cycle. So here we're hypothesizing that at the beginning of the solar cycle, where there's not yet magnetic fields, that you have some predominantly poloidal field. That's what you would need for the MRI. And then the MRI is then going to be able to generate these sorts of toroidal fields, which are mostly at mid latitudes, which would then lead to sunspots. And then also, if you look at the timescales of these modes, it seems to match up decently with the timescales of variability of the solar cycle. And also, you can use, this is a linear calculation, but you can do some sort of like quasi-linear analysis to guess the saturation of this. And that gives you magnetic field amplitudes that are similar to those that have been inferred with helioseismology. Good. Okay. So the next thing that I want to mention is angular momentum transport. And I'm going to think about this in the context of massive stars. And as I've already mentioned, massive stars, they have a convective core and a radiative envelope. Okay. And this is this is not the only system out there in nature where we have convection below a stable stratification, like a radiative zone. Another case where this occurs is the Earth's atmosphere. So in the Earth's atmosphere, you have convection in the lower layer, the troposphere. This is basically just storms. And then in the stratosphere is like the radiative zone of a star. It's stably stratified, so there's no convection there. Instead, you get the gravity waves. Okay, so this is a simulation where they have the convection and excites all these waves in the stratosphere. And it's known in the Earth's atmosphere that these waves are actually can be quite important for the global circulation. And in particular, they give rise to oscillating zonal winds. So in the equatorial region of the Earth, there's this zonal wind pattern where at low altitudes, so closer to the Earth, you might have winds going around in one direction, but then higher up, you have winds going around in the other direction. This, of course, is not to scale. Okay, but so it might look like for a certain amount of time, but then if you wait a little bit, it'll flip orientation, where basically the winds lower down will be this blue sign, and then the higher up winds will be the red sign. So to just show this in a diagram, these are some measurements of the zonal wind speed as a function of height and also of time. And you can see that's this characteristic pattern where, interestingly, the winds start aloft and then they actually propagate downwards. Okay? And this has been very steady. The period is about 28 months. So it's known as the quasi-biennial oscillation. It's not quite 2 years, close. And because of that, it's robustly different from 24 months. Okay, it's not due to seasonal variability. This is really due to waves that are excited by convection. This was observed since at least the 40s and has been very regular up until 2016, where there was a disruption. You can see that there's this blue phase here, propagate downward, red phase, propagate downward, blue, propagate downward, red. Okay, and then you started with a blue phase, but then it stopped. So there was a disruption in 2016, and then a second one in 2020. So we had this very regular record for over 50 years, and then all of a sudden, very recently, it's been changing. Okay. So of course, people think that this is related to climate change, but the details of what causes these disruptions and the overall oscillations are still not very well understood. In particular, none of the global climate models predicted what's going to happen. So they've all been tuned so that they can reproduce the historical record, but they're useless for making future predictions if it's different from what we've already seen. Okay, so that's on Earth, but the Earth isn't the only place that we see this. There's other systems out there where we have convective regions next to radiative zones, and another example of that would be Jupiter. And in Jupiter, we also see these types of mean flow oscillations. Now, in Jupiter, it's hard to actually measure the wind speed. So what people do is that they look at the temperature as a function of latitude. Okay? This is at one depth in Jupiter's atmosphere, and this is at a different depth. And basically, people look at what's going on at the equator. You can see that the temperature has this sort of curvature. It turns out that you can link the curvature to the vertical shear of the wind. Okay, so if the curvature is positive, that means that you have wind in one direction above and then the other direction below. Whereas if the curvature is negative, then it would be flipped. So the fact that the curvature is positive here and negative here tells you that in those 4 years that there was a flip in the sign of the shear, and that the winds flip directions. Okay. In this case, the oscillation time scale is about 4 years. So this is the first observations, but it has been confirmed and seen more recently. Here it's known as a quasi-quadrennial oscillation. And then another place where we've seen this is on Saturn. Okay. Now we want to use the same technique as Jupiter with Saturn, but the issue is that with Saturn the rings are blocking half of the planet. So you can't calculate the curvature. So instead, you look at the temperature at the equator, and then the temperature either a little bit to the south or a little bit to the north, depending on which side the rings are blocking. Okay, so we're assuming that it's about symmetric, and that there's some curvature. But if you do that, you can see that we have this oscillation here. Okay, the period is about 15 years. So any guesses on what they call that one? Anyone know their I don't know, is it Greek or Latin or something? Okay. This one they call the semi-annual oscillation. It turns out that the period of Saturn is about 30 years. This one they think is related to a seasonal cycle, okay? Because it's half of the year, okay? But on Earth and Jupiter, they think that that's not the case, that this is really just due to waves that are excited by convection. Okay, so this is angular momentum transport that we've observed in the Earth, Jupiter, maybe also Saturn, and we want to understand, could the same thing be happening in stars, and if so, what kinds of predictions would this make for what we might be able to see with asteroseismology? So in order to do this, with some collaborators, we've been trying to model this angular momentum transport problem by waves excited by convection. We start with a very idealized approach, but then as you'll see later, we've been able to apply this to more realistic simulations. So the first question is how do you end up with a configuration where part of your domain is convective and part is a radiative zone? So I want to recall that for normal fluids, there's an inverse relationship between temperature and density. But it turns out that water is a very strange fluid. The density maximum of water isn't at 0 degrees that you might expect, it's actually at 4 degrees. So the density of water as a function of temperature follows this sort of curve. So if you take a tank of water, cool it to 0 at the bottom, keep the top at room temperature, you can kind of think of temperature as being like a vertical coordinate. So in the lower part, you'll find that the temperature and also density is increasing with height, which means that you're unstable to convection because you have dense fluid above light fluid. So the dense fluid wants to fall, the light fluid wants to rise. Whereas above 4 degrees, the density is decreasing with height, and that's stable. Okay. Here you're going to get your gravity waves. This is like the radiative zone of a star. Okay. Here you have dense fluid, which is below light fluid. That's a stable configuration. So my collaborator, Michael Dedalus, actually ran a laboratory experiment of this. So he did this at UCLA, so not too far away, while he was on sabbatical. So this is his tank of water. You can see that there's this thermistor array. So he used that to measure the temperature as a function of height. And you can see the lower part of the tank is about 4 degrees. So it's about isothermal. The convection has mixed up the temperature here. And then the upper part of the tank, the temperature is increasing with height. So here you're stably stratified. This is like the radiative zone. Then you can see that there's this green laser sheet. He used particle imaging velocimetry in order to measure the velocities associated with these flows. So if you just look up here in the radiative zone, we expected to see waves, and that's exactly what we found. So these are the wave motions measured in his experiment. And the velocities are extremely small. It's about 10 microns per second. But they're coherent for long enough times that you can kind of integrate long enough to be able to measure these wave velocities. And we did verify that these satisfy the dispersion relationship of gravity waves. So these are really gravity waves. The issue with the experiment is that it's very hard to simultaneously measure the convection and the waves because the convection is much larger amplitude. So for that, we turn to numerical simulation, and that's with the Dedalus code. So this is something, a project that I've been involved with. I want to specifically mention Jeff Vassell, who's at University of Edinburgh, who developed most of the numerical algorithms, and Keaton Burns, who's a research scientist at MIT, who wrote most of the code. So Dedalus is a general PDE solver. The way that works is that you specify the partial differential equation that you want to solve as a string. So everything's in Python. So it turns out that these are the equations that we wanted to solve in order to model this water experiment. So we have a velocity equation, a temperature equation, and this incompressibility constraint. And the way that you implement these equations in Dedalus is as follows. So for this equation here, say that the time derivative of the velocity u plus the gradient of the pressure minus the Laplacian of the velocity. So Dedalus knows what all the normal vector calculus operations are. So like gradient, divergence, Laplacian, curl, etc. That's equal to negative u dot grad u. So the at symbol is the dot product. And then we have a buoyancy term here. So this is a control parameter times the vertical unit vector times t minus t naught squared, where t naught is 4 degrees. So that's to model the nonlinear equation of state of water, which we model as being locally parabolic. Okay, so this kind of shows you how you go from equations into this kind of like domain-specific language, and then Dedalus takes this and then is able to run a numerical simulation. Now, I want to note that that these equations are using what's called the Boussinesq approximation. So this convection simulation, and I guess we were at a conference dinner at KITP in Santa Barbara, and someone maybe had a few too many beers, and they asked themselves, what if instead of studying Boussinesq convection, we instead studied Boussinesq convection? So this is another simulation using Dedalus. So this is, if you imagine you had a 2-dimensional moose and you filled it with water, heated it at its hooves and cooled it at its antlers, then you would develop flows as shown here. Okay. So this is a Boussinesq convection. And in addition to being kind of a cute example, is actually a really nice test of a numerical algorithm, because these equations are being solved in polar geometry. That means that there's a coordinate singularity right there, but the flows go right through without any issues, and there's no time stepping problems associated with that. Okay, so this is actually a quite challenging numerical simulation to run, even though it's mostly for fun. So I mean, for me, this is my first foray into using Dedalus for biology, but many other people have as well. So here I'm showing the number of papers that have used Dedalus per year. So the first one was a paper I wrote in 2014. And what's been really cool is seeing that the code has been used by more and more people each year. We don't have the numbers yet for 2024 because we've been lazy, but there was also over 100 papers using Dedalus in 2024 as well. But not only are very many people using it, but it's also over a very wide range of fields. So to me, that's very exciting. People are using this to study problems I would never have thought of, like actual biology problems, as well as problems in material science, condensed matter physics, machine learning, and many other fields. Okay, so to turn back to this water tank experiment, we're able to run numerical simulations where we have both the convection here and the waves, and from the simulation you can analyze them together. Now, the thing is that this is not very realistic for what's going on in a star. So what we did was that we kind of took this 2-dimensional setup and tweaked it a little bit to make it 3-dimensional. So now we have our convection zone down here and your radiative zone up here. And 3-dimensional, and we were able to then study some of the theories out there for how the convection excites waves. So the theoretical prediction is that the wave energy flux is proportional to the convective energy flux. There's an efficiency factor, and then there's also a dependence on the frequency of the wave and the wave number of the wave. Okay, so you get these steep power laws minus 13/2 and plus 4. Okay, and we wanted to be able to test these in the numerical simulations. That's exactly what we did right here. So from those simulations that Louis Cousson ran, we measured the wave energy flux as a function of frequency. This is for 2 different wave numbers. The different curves are at different heights in the simulation. So this is near the interface with the convection zone, and as you move upwards, you can see you damp out low frequency waves, but the high frequency waves stay the same, and that matches the theoretical prediction. And then our minus 13/2 power law is this blue curve here, and you can see that seems to match up with the simulation data fairly well. Okay, now you might say, well, this doesn't really look like a star. So what Evan Anders did was that he ran a similar sort of setup in spherical geometry. So this is what we think is going on in a 15 solar mass star. So I'm plotting the radial velocity here in our spherical simulation, and then out here is temperature fluctuations in the radiative zone. And from these simulations, we're able to again measure the spectrum of waves excited by convection. So it turns out that our simple idealized simulation actually captured all the important physics, but just for completeness, we threw in like all of these names. Darken nicely with this minus 13 halves power law. Okay, so from this, we can now actually make some predictions about what we might expect in stars. So in particular, you might ask, can you observe these waves at the surface? These waves are going to produce brightness fluctuations at the surface, which might be observable with asteroseismology. Ultimately, what we found from our simulations is that the observed variability. So this is the photometric variability that we predict might be detected by tests, I think, here in micromags, is actually orders of magnitude less than some of the observed variability that we already see at the surface. So unfortunately, these waves are excited at fairly low amplitudes and thus cannot be directly detected. However, we do think that they might be important for stellar evolution, even if we can't directly detect them. So one way is that the waves can transport chemicals. So this is some recent work by Yifeng Mao, who's a postdoc at San Diego, UCSD. The waves might be able to produce magnetic fields. So they might be able to run a dynamo via Taylor-Sprout instability. And this is something that Lecoanet and Daniel worked on during his PhD. But I want to turn back to something that I mentioned for this issue of angular momentum transport. So what we were to do was now it's just two-dimensional, but we have convection down here, and then we have waves up here. So this is the radiative zone. At certain times in the simulation, the waves are all going upwards into the. But then if you let things run longer, the convection kind of stays pretty similar. But if you look at the waves, all of a sudden the pattern starts to change. Instead of the features going upwards into the right, the features are mostly going upwards into the left. So why is that? Well, it turns out that the waves are driving a mean flow. So now in this movie, we show the mean flow in black. And you can see that you start off with this mean flow that's to the left. And then that filters out the leftward going waves. And then you start to develop a mean flow to the right. So that filters out the rightward going waves, and it kind of oscillates back and forth. Okay. So in this simple model that I described, we're able to understand these mean flow oscillations. So this is exactly the mechanism that we think is occurring in the Earth's atmosphere. But then the question is, can this also happen in stars? So now Florent Daniel is at Northwestern. He's up there, and he's looking at this angular momentum transport problem now for more stellar type systems. So here we're doing it in polar geometry, and he's found that here as well we're able to get these mean flow oscillations. So this is the average mean flow as a function of radius and time, and you can see these characteristic patterns where mean flows develop in the outside layers and then propagate inwards towards the convection zone. Of course, the big question is, what's the amplitude and period of this, and could this be observed with, for instance, asteroseismology, or be important for stellar evolution? So that's kind of where I want to leave off. But the last thing that I want to mention is that I think that now is a very exciting time for stellar astrophysics. We've had all these recent space satellites that have made many different asteroseismic observations that have told us a lot about the interiors of stars, and more is coming soon. So Plato is scheduled to launch just next year, and I want to mention that the O in Plato stands for oscillation. So this is actually one of the main parts of the mission, is to do asteroseismology. And then the other thing that I want to note is that I think that in order to make the most use of these observations, we really need to be able to combine the 1D stellar modeling with 3D simulations of the type that I've shown you. So that's for instance, combining 1D codes like MESA with Dedalus, or for instance, Athena is good for studying the surface layers of stars. And I think that through this, we'll be able to understand the much better, and then be able to understand these processes like chemical transport, dynamos, and angular momentum transport that are so important for modeling stars for many different astrophysical applications. Thanks.
All right, good time for a few questions. Yeah. For the surface modes, do they interact with the upper boundary, and what do you think the picture of this?
Yeah, that's a great question. So, so I guess the way that we make predictions about the variability of these stars is that we run the numerical simulations to try to understand how the convection excites waves, and then to figure out what actual amplitude you end up getting. You need to have a balance between the wave excitation and a wave damping process. For these modes, the wave damping just comes from radiative diffusion. So what we do is that we use a stellar oscillation code, in particular gyre, in order to solve for what the oscillation modes would be of this star, and then to calculate the damping rates associated with that. So and in that case, gyre uses specific boundary conditions that they think are decent for modeling what's going on near the surface of the star. But of course, it's not perfect.
Two things exoplanet people like about asteroseismology is getting the ages of the host stars. To what extent is it going more about these more subtle effects that play into affecting something like the age or the interior structure?
Yeah, that's a great question. Yeah, so I think that so these issues with chemical transport are particularly important for massive stars because the chemical transport is able to bring fresh fuel into the core where you have burning. It's not so important for more solar mass stars because in that case the core is fairly insulated from the convection because it's radiative. But one place where this is extremely important is for M dwarfs. There's lots of questions about how to correctly model the sizes of M dwarfs. It doesn't match with the predictions of stellar evolution models very well, and that's actually related. It's thought to be related to the presence of magnetic fields. So for sure, understanding how magnetic field influences energy transport in stars would play a big role in being able to better model M dwarfs, which of course is very important for exoplanets.
By solar dynamics. What is interesting is, I mean, similar effects have recently been simulated for binary mergers for neutron stars and white dwarfs, showing exactly the same thing. On the right, with the dynamo on the outer layer, the ultimate breakout. Where however there it's more dramatic in the sense that you have these large coherent modes that break out massive coronal mass ejection and drive a jet and like that. I wonder if your model for the sun, because that's thank you for us not with that. The question is then, what actually sets the coherent length that you produce, but that's the frequent breakout. Is your model able to make a prediction and connect that to the sun?
That's a great question. Can our model make a prediction of that? No. That's a very nonlinear effect. So something that we're working on is to branch from our current linear analysis and quasi-linear analysis to doing full nonlinear simulations to understand the real saturation of the instability And I think that will be very important for subsequently setting different length scales in the problem for sure.
Well, I
was also going to ask about other stuff.
Yeah, so luckily, I mean, that's something that's very well observed in the sun via helioseismology. So we use the observed shear profile for. So the helioseismology, what's the average rotation rate as a function of radius and latitude, but it also shows that there's oscillations in that over the solar cycle. And we're able to with our quasi-linear analysis match the amplitude of those oscillations with what's observed, and also the oscillations that are seen that are tied to the solar cycle. Those seem to start off at the surface, not deeper down in the convection zone. So we think that that's some more evidence that that there might be dynamo action happening near the surface of the sun.
Okay, well, we have wine and cheese and champagne toast outside. Let's thank Daniel again.